So this is chapter 20, Chemical Texture Surfaces, and this is the first video. Our learning objectives in chapter 20 are 1. Explain the 4 chemical reactions that take place during permanent waving. 2. Explain the difference between an alkaline wave and a true acid wave. 3. Explain the purpose of neutralization in permanent waving. 4. Demonstrate safe and effective perm techniques. 5. Describe how thiorelaxers straighten the hair. 6. Describe how hydroxide relaxers straighten the hair. 7. Demonstrate safe and effective hydroxide relaxing techniques. And 8. Describe curl reforming and how it restructures the hair. Why study chemical texture surfaces? Cosmetologists should study and have a thorough understanding of chemical texture surfaces because chemical texture surfaces allow stylists the opportunity to offer clients options to change the texture of their hair and explore the fashionable world of hairstyling. Knowing how to perform these surfaces accurately, safely, and professionally will help build a trusting and loyal clientele. Knowledge builds confidence to offer chemical texture surfaces to all clients. Chemical surfaces are among the most lucrative and repetitive surfaces in the salon, and many retail products are specific to hair's texture and condition. Without a thorough understanding of chemistry, cosmetologists could damage hair, cause hair loss, and harm their clients and themselves. Chemical texture surfaces are hair surfaces that cause a chemical change within the hair's natural wave and curl pattern. They include permanent waving, adding wave or curl to the hair, relaxing, removing curl or waves, leaving the hair smooth and straight, and curl reforming, soft curl permanence, loosening overly curly hair, changing tightly curly or coiled hair into loose curls or waves. The world of hairstyling is ever-changing. Clients will always want to smooth their curly and wavy hair or give their straight hair more body and curl. Therefore, mastering the techniques in this chapter will allow you to greatly expand your potential as a cosmetologist. Understand how chemical surfaces affect the structure of hair. Because all chemical texture procedures involve chemically and physically changing the structure of the hair, this chapter begins by reviewing structure and purpose of each layer of the hair. Characteristics of hair that were first discussed in chapter 11. Properties of the hair and scalp. First, cuticle. Tough exterior layer of the hair. It surrounds the inner layers and protects the hair from damage. Although the cuticle is not directly involved in the texture or movement of the hair, texture chemicals must penetrate through the cuticle to their target in the cortex in order to be effective. Cortex. The middle layer of the hair located directly beneath the cuticle layer. The cortex is responsible for the incredible strength and elasticity of human hair. Breaking the side bonds of the cortex makes it possible to change the natural wave pattern of the hair. The medulla, the innermost layer of the hair, often called the pith or core of the hair. The medulla does not play a role in chemical texture surfaces and may be missing in fine hair. For more detailed information on the hair structure, review Chapter 11, Properties of the Hair and Scalp. The importance of pH in texture surfaces. In Chapter 12, Basics of Chemistry, you learned that pH is an abbreviation for potential hydrogen. The symbol pH represents the quantity of hydrogen ions. The pH scale measures the acidity and alkalinity of a substance by measuring the quantity of hydrogen ions it contains. The pH scale has a range from 0 to 14. A pH of 7 is neutral. A pH below 7 is acidic, and a pH above 7 is alkaline. The natural pH of hair is between 4.5 and 5.5. Chemical solutions raise the pH of the hair to an alkaline state. This action opens the cuticle layer of the hair and allows the solution to reach the cortex layer, where restructuring occurs. Coarse, resistant hair with a strong, compact cuticle layer requires a highly alkaline chemical solution. Porous, damaged, or chemically treated hair requires a less alkaline solution. Basic building blocks of hair. To understand how a chemical solution changes the structure of hair, it is important to understand the basic building blocks of hair. And you might want to look to figures 20 through 5, 20 number 5 through 20-number 8. Amino acids are compounds made up of carbon, oxygen, hydrogen, nitrogen, and sulfur. Peptide bonds, also known as end bonds, are chemical bonds that join amino acids together end to end in long chains to form a polypeptide chain. Polypeptide chains are long chains of amino acids joined together by peptide bonds. Keratin proteins are long coiled polypeptide chains. And side bonds are disulfide, salt, and hydrogen bonds that cross-link polypeptide chains together. Keratin proteins are made of long chains of amino acids linked together end to end like beads. These chains of amino acids linked by peptide bonds are called polypeptides. Keratin proteins are made of long, coiled polypeptide chains, which in turn are comprised of amino acids. Side bonds. The cortex is made up of millions of polypeptide chains cross-linked by 3 types of side bonds: disulfide, salt, and hydrogen. Side bonds are responsible for the elasticity and strength of the hair. Altering these 3 types of side bonds makes wet setting, thermal styling, permanent waving, curl reforming, and chemical hair relaxing possible. Disulfide bonds. Disulfide bonds are strong chemical side bonds formed when the sulfur atoms in 2 adjacent protein chains are joined together. Although these are far fewer disulfide bonds than hydrogen or salt bonds, although there are far fewer disulfide bonds than hydrogen or salt bonds, they are the strongest of the 3 side bonds, accounting for about 1/3 of the hair's overall strength. Disulfide bonds are not affected by water. However, boiling water can break and alter their appearance. Although the amount of heat used in conventional thermal styling does not break disulfide bonds, caution must be used when using thermal tools with extreme heat, because the high heat can cause irreversible damage to the hair. Altering the chemical and physical changes in disulfide bonds makes permanent waving, curl reforming, and chemical hair relaxing possible. Salt bonds. Salt bonds are relatively weak physical side bonds that are the result of an attraction between negative and positive electrical charges, ionic bonds. They are easily broken by changes in pH, and they reform when the pH returns to normal levels. Hydrogen bonds can be broken by water, whereas salt bonds are broken by changes in pH levels. Even though salt bonds are far weaker than disulfide bonds, the hair has so many salt bonds that they account for about 1/3 of the hair's total strength. Hydrogen bonds. Hydrogen bonds are weak physical side bonds that are also the result of an attraction between opposite electrical charges. They are easily broken by water, wet setting, or heat, thermal styling, and they reform as the hair dries or cools. Although individual hydrogen bonds are very weak, there are so many of them that they too account for about 1/3 of the hair's total strength. Okay, next section. To demonstrate the proper technique for permanent waving. Permanent waving is a two-step process whereby the hair undergoes a physical change caused by wrapping the hair on perm rods. The hair then undergoes a chemical change caused by the application waving solution and neutralizer. Because chemical changes are involved, you should always perform an elasticity test before perming the hair. When performing a permanent waving service, the size of the rod determines the size of the curl. The shape and type of curl are determined by the shape and type of rod and the wrapping method used. Selecting the correct perm rod and wrapping method is crucial to creating a successful permanent wave. Perm rods come in a wide variety of sizes and shapes that can be combined with different wrapping methods to provide an exciting range of hairstyling options. The chemistry of permanent waving. Alkaline permanent waving solutions soften and swell the hair, and they open the cuticle, permitting the solution to penetrate into the cortex. Figure 20-12 illustrates hair saturated with alkaline permanent waving solution, pH 9.4 for 5 minutes. Note the swelling of the cuticle layer. In figure 13-20-13, hair from the same sample has been saturated with acid balanced waving solution, pH 7.5 for 5 minutes. Note that there is far less swelling of the cuticle layer. Reduction reaction. Once in the cortex, the waving solution breaks the disulfide bonds through a chemical reaction called reduction. A reduction reaction involves either the addition of hydrogen or the removal of oxygen. I'm going to repeat that. A reduction reaction involves either the addition of hydrogen or the removal of oxygen. The reduction reaction in permanent waving is due to the addition of hydrogen. I'll repeat that. The reduction reaction in permanent waving is due to the addition of hydrogen. The chemical process of permanent waving involves the following reactions. A disulfide bond joins the sulfur atoms in two adjacent polypeptide chains. Permanent wave solution breaks a disulfide bond by adding a hydrogen atom to each of its sulfur atoms. The sulfur atoms attach to the hydrogen atom from the permanent waving solution, breaking their attachment to each other. Once the disulfide bond is broken, the polypeptide chains can form into their new curled shape. Reduction breaks disulfide bonds and oxidation reforms them. All permanent wave solutions contain a reducing agent. The reducing agent, commonly referred to as THIO, T-H-I-O, THIO, is used in permanent waving solutions. It contains a thiol, T-H-I-O-L, thiol, which is a particular group of compounds along with carboxylic acid, carboxylic, I think is probably how it's pronounced, carboxylic. And now we have a section on thioglycolic acid. I believe the pronunciation is thioglycolic acid. A colorless liquid with a strong, unpleasant odor is the most common reducing agent in permanent wave solutions. The strength of the permanent waving solution is determined primarily by the concentration of thio. Stronger perms have a higher concentration of thio, which means that more disulfide bonds are broken compared to weaker perms. Because acids do not swell the hair nor penetrate into the cortex, it is necessary for manufacturers to add an alkalizing agent. The addition of ammonia to thioglycolic acid produces a new chemical named ammonium thioglycolic, which appears to be ATG. Ammonium thioglycolic, AMMONIUM, it's two words, and then thioglycolic, THIOGLYCOLATE, thioglycolate, ammonium thioglycolate, ATG. It's an alkaline and is the active ingredient or reducing agent in alkaline permanents. The degree of alkalinity, pH, is a second factor in the overall strength of the waving solution. Coarse hair with a strong resistant cuticle layer needs the additional swelling and penetration that is provided by a stronger and more highly alkaline waving solution. By contrast, porous hair or hair with a damaged cuticle layer is easily penetrated and could be damaged by a highly alkaline permanent waving solution. The alkalinity of the perm solution should correspond to the resistance, strength, and porosity of the cuticle layer. Types of permanent waves. A variety of permanent waves are available in salons today. Brief descriptions of the most commonly used perms are as follows, though you might want to refer to figure 20-15, which shows the range of permanent waves going from a 6.5 to 7.0 low pH waves all the way up to an extreme 9.0 to 9.6 pH waves. But we will discuss each of these, starting with alkaline waves or cold waves. Alkaline waves, also known as cold waves, were developed in 1941. They have a pH between 9.0 and 9.6. Ammonium, ATG, ammonium thioglycolate is the reducing agent, and it processes at room temperature without the addition of heat. Acid waves. Glycerol monothioglycolate, glycerol monothioglycolate, so it appears to be called GMTG. The spelling is glycerol, Glyceryl, glycerol. Mono, M-O-N-O, Thio, Glycolate, so two words, glycerol monothioglycolate, GMTG. Is the main active ingredient in true acid and acid-balanced waving lotions. It has a low pH and is the primary reducing agent in most acid waves. Most acid waves also contain ATG, just like a cold wave. Although the low pH of acid waves may seem ideal, repeated exposure to GMTG is known to cause allergic sensitivity in both hairstylists and clients. Repeated exposure to GMTG, glycerol monothioglycolate, is known to cause allergic sensitivity in both hairstylists and clients. True acid waves. All acid waves have three separate components: permanent waving solution, activator, and neutralizer. The activator tube contains GMTG, which must be added to the permanent waving solution before applying to the hair. The first true acid waves were introduced in the early 70s. I got interrupted, so I'm going to go back. True acid waves. All acid waves have three separate components: permanent waving solution, activator, and neutralizer. The activator tube contains GMTG, which must be added to the permanent waving solution before applying to the hair. The first true acid waves were introduced in the early 70s. True acid waves have a pH between 4.5 and 7.0 and require heat to process. They process more slowly than alkaline waves, and they do not usually produce as firm a curl as alkaline waves. GMTG, which has a low pH, is the active ingredient. Since acidic solutions contract the hair, you may be wondering how a true acid wave with a pH below 7.0 can cause the hair to swell. Although a pH of 7.0 is neutral on the pH scale, a pH of 5.0 is neutral for hair. The pH of any substance is always a balance of both acidity and alkalinity. Even the strongest acid also contains some alkalinity. And again, they're sending you back to chapter 12 to review the pH scale, basics of chemistry. Acidity increases when alkalinity decreases, and alkalinity increases when acidity decreases. Because every step in the pH scale represents a tenfold change in pH, a pH of 7.0 is 100 times more alkaline than a pH of hair, 5.0. Even pure water with a pH of 7.0 can damage the hair and cause it to swell. This is a confusing paragraph. I think this is the paragraph that you were identifying as confusing. Because every step in the pH scale represents a tenfold change in pH, a pH of 7.0 is 100 times more alkaline than a pH of hair 5.0. Even pure water with a pH of 7.0 can damage the hair and cause it to swell. Acid-balanced waves. In order to permit processing at room temperature and produce a firmer curl, the strength of pH of acid waves have increased steadily over the years. Most of the acid waves found in today's salons have a pH between 7.8 and 8.2. Modern acid waves are actually acid-balanced waves, which are permanent waves that have a 7.0 or neutral pH. Because of their higher pH, they process at room temperature, do not require the added heat of a hairdryer, process more quickly, and produce firmer curls than true acid waves. Exothermic waves. An exothermic chemical reaction produces heat. Exothermic waves create an exothermic chemical reaction that heats up the waving solution and speeds up the processing. All exothermic waves have three components: permanent waving solution, activator, and neutralizer. I'm going to repeat that. All exothermic waves have three components: permanent waving solution, activator, and neutralizer. The permanent waving solution contains thio, just as in a cold wave. The activator contains an oxidizing agent, usually hydrogen peroxide, that must be added to the permanent waving solution immediately before use. Mixing an oxidizer with the permanent waving solution causes a rapid release of heat and an increase in the temperature of the solution. The increased temperature increases the rate of the chemical reaction, which shortens the processing time. Endothermic waves. An endothermic chemical reaction is one that absorbs heat from its surroundings. Endothermic waves are activated by an outside heat source, usually a conventional hood-type hairdryer. Endothermic waves will not process properly at room temperature. Most true acid waves are endothermic and require the added heat of a hairdryer. Ammonia-free waves. Ammonia-free waves are perms that use an ingredient that does not evaporate as readily as ammonia, so there's very little odor associated with their use. There's a word here, AMP it appears what most people call it, but it's aminomethypropanol, or AMP, and monoethanolamine, monoethanolamine, or MEA, monoethanolamine. So AMP and MEA are examples of alkylamines that are used in permanent waving solutions as a substitute for ammonia. Even though these solutions may not smell as strong as ammonia, they can still be every bit as alkaline or just as damaging. Remember, ammonia-free does not necessarily mean damage-free. Thio-free waves. Thio-free waves use an ingredient other than ATG, such as cysteamine, 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 or mercaptamine, mercaptamine, mercaptamine. So thio-free waves uses an ingredient other than ATG, such as cysteamine or mercaptamine, as the primary reducing agent. Even though these thio substitutes are not technically ATG, they are still thio compounds. Although thio-free wave products are often marketed as damage-free, this is not necessarily true. At a high concentration, the reducing agents in thio-free waves can be just as damaging as thio. Low pH waves. The use of sulfites, and bisulfites presents an alternative to ATG known as low pH waves. Sulfites work at a low pH. They have been used in perms for years, but they've never been very popular. Permanents based on sulfites are very weak and do not provide a firm curl, especially on strong or resistant hair. Sulfite permanents are usually marketed as body waves or alternative waves. Selecting the right type of perm. It's extremely important to select the right type of perm for each client. Each client's hair has a distinct texture and condition, so individual needs must always be addressed. After a thorough consultation, you should be able to determine which type of permanent is best suited to your client's hair type, condition, and desired results. Table 20-1 lists the most common types of permanent waves along with recommended hair type for each, so you might want to study that. 20-1. These are only general guidelines. Perms for use on color-treated hair are not necessarily safe for damaged or bleached hair. Also, hair that has been treated with semi-permanent color, which coats the hair, is not as porous as hair treated with permanent color and may actually appear more resistant. permanent wave processing. The strength of any permanent wave is based on the concentration of its reducing agent. In turn, the amount of processing is determined by the strength of the permanent wave solution. If a mild permanent wave solution is used on coarse hair, there may not be enough hydrogen ions to break the necessary number of disulfide bonds, no matter how long the permanent process is. In other words, the perm solution chosen would be incorrect. But the same mild solution may be exactly right for fine hair with fewer disulfide bonds. On the other hand, a strong solution, which releases many hydrogen atoms, may be perfect for coarse hair, but too harsh and damaging for fine hair. The amount of processing should be determined by the strength of the solution, not necessarily the perm's processing time. In permanent waving, most of the processing takes place as soon as the solution penetrates the hair, within the first 5 to 10 minutes. The additional processing time allows the polypeptide chains to shift into their new configuration. If you find that your client's hair has been overprocessed, it probably happened within the first 5 to 10 minutes of the service. Within the first 5 to 10 minutes of the service, and a permanent waving solution should have been used. If the hair is not sufficiently processed after 10 minutes, it may require a reapplication of waving solution. Resistant hair requires a stronger solution, a higher pH, and a more thorough saturation. It must be noted that saturation of the hair is essential to ensure proper processing for a permanent wave service, regardless of the strength of the solution. Resistant hair may not become completely saturated with just one application of waving solution due to the density of the hair's structure. Therefore, reapply the solution slowly and repeatedly until the hair looks wet and stays wet. Overprocessed hair. A thorough saturation with a stronger, more alkaline solution will break more disulfide bonds and process the hair more. But processing the hair more does not necessarily translate into more curl. A properly processed permanent wave should break and rebuild approximately 50% of the hair's disulfide bonds. I'm going to repeat that. Properly processed permanent wave should break and rebuild approximately 50% of the hair's disulfide bonds. If too many disulfide bonds are broken, the hair may not hold the desired curl. Weak hair equals a weak curl. Overprocessed hair usually has a weak curl pattern and may appear to be absolutely straight. Great. Since the hair at the scalp is usually stronger than the hair at the ends, overprocessed hair is usually curlier at the scalp and straighter at the ends. You can see a picture of this, figure 20-18. If the hair is overprocessed, further processing will make it straighter and cause further damage, including breakage. Underprocessed hair. Underprocessed hair is the exact opposite of overprocessed hair. If too few disulfide bonds are broken, the hair will not be sufficiently softened and will not hold the desired curl. Underprocessed hair usually has a very weak curl, but it may also be straight. Since the hair at the scalp is usually stronger than at the ends, underprocessed hair is usually straighter at the scalp and curlier at the ends. If the hair is underprocessed, further processing will make it curlier. Permanent waving thioneutralization. In permanent waving, thioneutralization stops the action of the waving solution and rebuilds the hair into its new curly form. Neutralization performs two important functions. Any waving solution that remains in the hair is deactivated, meaning neutralized. And disulfide bonds that were broken by the waving solution are rebuilt. The neutralizers used in permanent waving are oxidizers. In fact, the word neutralizer is not accurate because the chemical reaction involved is actually oxidation. The most common neutralizer is hydrogen peroxide. Concentrations vary between 5 volume, which is 1.5%, and 10 volume, which is 3%. The neutralization, stage 1. The first function of permanent waving, neutralization, is the deactivation or neutralization of any waving lotion that remains in the hair after processing and rinsing. The chemical reaction involved is called oxidation. Given that water's pH is between 6 and 7, rinsing begins the neutralizing process. Proper rinsing and blotting are important. Prior to applying the neutralizer, properly rinsing the hair after the permanent has processed removes any remaining perm solution. Oxidative reactions can also lighten hair color, especially at an alkaline pH. To avoid scalp irritation and unwanted lightening of hair color, always rinse perm solution from the hair for at least 5 minutes, and then blot the hair with towels to remove as much moisture as possible. Excess water in the hair reduces the effectiveness of the neutralizer. A successful perm requires knowledge, time, and patience. And there are several bullets of steps of a successful perm. First, always rinse the hair with warm water, never hot water. Second, always use a gentle stream of water, never a strong blast of water. Never apply pressure to the rods while rinsing out the solution. Always begin rinsing at the area where you first applied the perm solution, with the most fragile areas typically at the temple and hairline. Always check the nape area to ensure that you are thoroughly rinsing the bottom rods. Always rinse for the time recommended by the manufacturer. Always smell the hair after the recommended time has elapsed. If it still smells like perming solution, continue rinsing until the odor is gone. Always gently blot the hair with a dry towel, never firmly or aggressively blot the hair, as it could disrupt the curl blocking pattern after the final wave or curl. Always check for excess moisture, especially at the nape of the neck where water tends to accumulate, prior to neutralizing the hair. Always adjust any rods that have become loose or have drifted out of alignment prior to applying the neutralizer. It's probably worth backing up and rereading each of those items. Okay, some manufacturers recommend the application of a pre-neutralizing conditioner after rinsing and blotting, just before application of the neutralizer. An acidic liquid protein conditioner can be applied to the hair and dried under a warm hair dryer. Hair is uncovered. Always follow manufacturer's instructions. For 5 minutes or more prior to neutralization. This added step is especially beneficial for very damaged hair because it strengthens the hair prior to neutralization. Always follow the manufacturer's directions and the procedures approved by your instructor, of course. Thioneutralization stage 2. As discussed, permanent waving solution breaks disulfide bonds by adding hydrogen. Thioneutralization rebuilds the disulfide bonds by removing the hydrogen that was added by the permanent waving solution. The hydrogen atoms are strongly attracted to the oxygen in the neutralizer and release their bond with the sulfur atoms and join with the oxygen. Each oxygen atom joins with 2 hydrogen atoms to rebuild one disulfide bond, forming a water molecule. The water is removed in the final rinse. Side bonds are then reformed into their new shape at different pairs. Permanent waving procedures. Preliminary test curls. Preliminary test curls help you determine how your client's hair will react to a perm. It is advisable to do preliminary test curls to assess what the final curl pattern will look like. This is especially important if the hair appears damaged, dehydrated, color treated, or if there's any uncertainty about the results. Preliminary test curls provide the following information and answer the following questions. Correct processing time for the best curl development. Results you can expect from the type of perm solution selected. Curl results for the rod size and wrapping technique you are planning to use. Will the integrity of the hair be compromised? Did the hair break? Is it dry? Is it frizzy? Is the client satisfied with the shape and hold of the curl? The following is a discussion about the types of rods. The concave rod, C-O-N-C-A-V-E, are the most common type of perm rod. They have a smaller diameter in the center that increases to a larger diameter at the ends. Concave rods produce a tighter curl in the center and a looser curl on either side of the strand. Straight rods are equal in diameter along their entire length or curling area. This produces a uniform curl along the entire width of the strand. Both concave and straight rods come in different lengths to accommodate different sections on the head. Short rods, for instance, can be used for wrapping small and awkward sections where long rods would not fit. Soft bender rods. Soft bender rods are usually about 12 inches, 30 centimeters long with a uniform diameter along the entire length of the rod. These soft foam rods have a flexible wire inside that permits them to be bent into almost any shape. You might want to look at figure 24, 20-24. I can't believe that they're 12 inches long. That's a foot. Maybe that's a typo. The loop rod, also known as circle rod, is usually about 12 inches, 30.5 centimeters. So this is also 12 inches long with a uniform diameter along the entire length of the rod. After the hair is wrapped, the rod is secured by fastening the ends together to form a loop. Okay, look at figure 20-25. Today, many perms are performed with large rollers, rag rollers, or other tools in order to achieve large, loose curls and wave. Larger tools are also used for root perms, in which only the base of the hair is permed to create volume and lift without curl. End papers. End papers, also known as end wraps, are thin, absorbent papers used to control the ends of the hair when wrapping and winding hair on the perm rods. End papers should extend beyond the ends of the hair to keep them smooth and straight and to prevent fish hooks, hair that is bent up at the ends. The most common end paper techniques are the double flat wrap, single flat wrap, and bookend wrap. The double flat wrap is a perm wrap in which one end paper is placed under and another is placed over the strand of hair being wrapped. Both papers extend past the hair ends. This wrap provides the most control over the hair ends and also helps keep them evenly distributed over the entire length of the rod. You might want to look at the pictures, figures 20-26, -27, -28, and -29. It's kind of interesting. The single flat wrap is similar to the double flat wrap, but uses only one end of paper, placed over the top of the strand of hair. The bookend wrap uses one end paper folded in half over the hair ends like an envelope. The bookend wrap eliminates excess paper and can be used with short rods or with very short lengths of hair. When using this wrap method, be careful to distribute the hair evenly over the entire length of the rod. Avoid bunching the hair in the fold of the paper. Hair should be in the center to produce an even curl.